Thank you very much for the space. So I will be presenting a work that we've done together with my student and my colleague, who are also named on the slide, where the idea of it was that in the context where we are at the moment, that's the Czech Cybercrime Center of Excellence, we see that the complexity of the systems nowadays that needs to be secure and reliable and dependable is actually growing so much that at the moment it is very hard to get a person who has just keeping an eye on everything at once. So what is actually happening is that we have people with fragmented view of what is being with that system secured and taken care of. And there came an idea that it would be actually very nice to have a kind of a checklist to make sure that nothing crucial or important wasn't forgotten. This also came to be very useful in the context of our collaboration with many external partners, because being an institute that is having that expertise and knowledge on the securing large infrastructures and systems that are highly complex, we are being approached by also companies that are running critical systems, asking for an advice, like could you take a look at the systems we are running, and is there something that we are forgetting? So there came this idea, okay, we could take a look at that. We could take a look at it. Of course, it's a huge task to do a checklist, like what is the whole thing that a system should think about if they are critical systems. So we were thinking actually, let's like try to pitch this idea and try to do a preliminary checklist like that. So we started working on the topic with a student, and to like focus a little bit, we were thinking, okay, so let's focus on systems that are critical. So let's take a look at the kinds of systems that we are running at the society level nowadays. These are called critical infrastructures, and these are typically systems that nowadays are getting more and more complex with highly cyber-physical elements connected to it, where certain pieces can be remote controlled. There are many devices that can be connected to those infrastructures that might come from third parties, possibly untrusted. So we first kind of like understood the complexity of these systems. To give you just a better picture, when we are speaking about critical infrastructures, the examples include, for example, smart grid, so the energy systems, or healthcare systems, right, where human lives depend on it, or transportation systems. And in each of these domains, and this is just a few examples, it's not a complete list, you can go deeper. So in transportation, of course, you have specific systems that are running the public transport, you have autonomous driving cars and the infrastructures around that, you have traffic management systems, etc. What is interesting on these systems for us is actually the software layer, because when I mentioned the system of this cybercrime and cybersecurity center of excellence, then we are a software department basically. And that is very useful to say, because very often one could say, okay, but standards exist how to run or design these infrastructures. But unfortunately, these standards disproportionately focus on the like embedded parts and segments of those systems, and very little on those like more soft and more flexible software that is running on those systems. So one of those things that, for example, our institute is doing is that energy distribution company comes to us and say, we have many experts who can actually operate on that security on the physical layer of the smart energy networks, but we do not really have the expertise of the security and reliability on that software layer that comes to these infrastructures. So that is our focus. Like, okay, so let's say that we have a software architect or software engineer who should give this kind of feedback to a system from the software point of view. Is there something missing, or is there something that the designer of the whole infrastructure has forgotten about? And that is becoming really complex because obviously, as I mentioned, there are many things to consider. Some things to consider is that we have plentiful of quality criteria. And obviously, you will have different standards when you care about security, different standards when you care about safety, different standards when you care about robustness, reliability, etc. And these are largely fragmented. Then you have different kinds of those infrastructures, right? As I mentioned, and again, a reason for another fragmentation of knowledge. And then what comes to it is actually that some of these qualities can be violated unintentionally, but some of them can be violated intentionally. And again, actually, the approach changes whether the problem was done as intentional or unintentional. This complexity is further strengthened by the fact that actually we have a highly hyperconnected world, highly distributed environments. And when building these systems, and that was a very interesting learning for me actually when talking to these, for example, energy distribution companies, is that we are building these systems to actually stably work for the next 20 or 30 years. While we have very little information, what will be the threats and the risks that these systems will be facing in actually 2 or 3 years' time. So what is very important for a software engineer or software architect when working on these systems is that they need to protect these systems against threats that are not existing yet, right? So what we did is that we start looking into some more general guidelines and principles that could be followed for these systems to be prepared for what we call engineering for the unknown. So the engineering for the unknown has like one important point to make, and that is that while these standards that are existing for the critical infrastructures are mainly looking into problem avoidance, we actually, if we want to engineer these systems for the unknown, we need to think about how to work under the assumption that we failed in problem avoidance, right? Because there will be smart workarounds of any kind of mechanisms that we will build in now that would avoid the attacker or some problem caused by a natural disaster entering the system. So just a few examples. So when you're engineering such a system, it's not sufficient to work for problem avoidance, but you need to actually be able to recognize that an attacker or a fault penetrated into the system, and then be able to detect that situation, understand how severe the situation is, stop this problem from propagating, contain it within some safe space, ensure safety when an ongoing attack is happening, and then be able to recover from it and be able to find out what happened, why it happened, who caused it, who is responsible, and how to prevent it for the future. Now, these things are something that is existing, but for incident handling. So actually how the systems work nowadays is that when a problem occurs, we are able to do this runtime mainly with an expert team that is able to say, yes, something is happening, and can actually jump on the project and try to recover, etc. While what we believe we need to do for the future is to pre-build mechanisms that are able to actually do that while the system is running without an expert team, like jumping in and solving the problem. So actually, when we think about such a checklist, we should have a pre-built mechanisms that allow for these things to be taken care of. And just an example that this is really not done and not solved from the last point in this list. So forensic readiness. What happens nowadays, and you can see it in infrastructures that are running in industry, is that when an attacker gets into the system and something really comes to a failure of a system, then what happens next is that there is a team trying to recover what was the source of the problem, how this happened, who is responsible, where did we go wrong, what failed, and they typically find out that there is not enough information. Because when designing these systems, we were not thinking proactively to log the right information, or even if we logged the right information, then we were not able to protect the integrity of those logs. So the attacker was able to actually delete the information that could be used as an evidence admissible at court to, for example, indicate that one of the insiders in the organization leaked some information or leaked some credentials to access some part of the system. So we were looking into this. Okay, so actually it would be very useful to have like a general checklist, like these are the things that you are forgetting about that could be used also by industry. And some just fun fact, if you know Ivar Jakobsen, who is the author of the UML language, he likes this saying of like the power of checklist, and the example he's using is the glove of Neil Armstrong, who was actually having the checklist for running the Apollo on his glove. This shows one important thing, and that no matter how smart we are, we always tend to forget the essentials if we are just focused on the complexity of the problem we have at hand. So it's like very useful to have a checklist. However, the checklist to be useful, it needs to fit on the glove, right? So if it was super complex, it wouldn't really fit the purpose. And for that, we were thinking about, okay, so like how we could create a checklist that says these are the crucial segments or elements not to forget about. But then if you actually want to go into the detail, for this one, follow this source. For this one, follow this source. For this one, follow this source. And that was the idea that we are trying to put in place. So to do that, we actually collect existing standards. We were trying to look into what kind of standards exist that we could include in that composition. When actually looking into that, we wanted to have the strong focus on the software part of those systems rather than the hardware. And we selected some representatives. We're trying to cluster the information we identified. So really actually pick the individual guidelines and try to structure the guidelines. For the categories of the checklist, we followed different, again, categorization schemes, and we arrived something that is following actually similar structure that I just described when I was speaking about this like incident handling, but preparedness for it. And I would say this is how it's also different from the standards existing. So we are speaking about how to do pre-built mechanisms when designing the software so that the software is ready to then be able to deal with the problem that is happening at runtime. So then we were trying to tag and cluster the information that information is in the paper and in the supplementary material. The phases in which we were trying to cluster the guidelines were the prevention, so basically protecting the attacker from getting into the system, then detection, so detecting that they are there, containment, so whenever you know that you have an attacker in the system, you need to be able to contain so that the attack does not spread within the system, do the automated recovery and post-incident analysis. And the same is true actually not only for those intentional like security problems, but also unintentional. So the same way, if you have an error propagating through the system, you do the same phases actually. So you want to prevent that problem from entering the system, but then once it is there, it very likely propagates. You want to do the detection, containment, recovery, and post-incident analysis. We introduce some tags for the guidelines so that we can cluster them, and then some examples of those guidelines represented in the paper. But let's say it was a position paper, it was just an attempt in this direction, and we would be very happy if somebody continued with that, because we find that very important and useful. So some examples and just like overviews. So for example, when you look at the prevention, so what you mainly need to do is to be able to protect your gateways. You are protecting your gateways by different means, and we have collected, this is just an excerpt, right? Like this is not the full table, this is just like a part of it, but I will tell you like bits and pieces of the information for those individual phases. So when you are preventing, you are really like securing the entry points to the system, and you can do it on different ways. We have clustered them based on those tags of the authorization, authentication, data protection, etc. Now, when you are in that phase of detecting, so that happens very often. There is a problem in your system, but you are not aware of it, and that's the state of the practice. Actually, unfortunately, that very often there is an error propagating through the system, and nobody knows about that. The same way there is an attacker propagating through the system, and nobody knows about it. There was this case. I don't know if you were following in 2015 in Ukraine. There was a attack on a Ukrainian power grid. Very likely it was actually directed from the Russia, as suspected also by some US forces that were trying to investigate that incident. But what happened is that they actually discovered that for half a year, 6 months, the attackers were moving through the system without anybody knowing or noticing, and they were opening the back door so that when the attack was like full-fledged actually triggered, there were no protective mechanisms active to prevent this from really deactivating hundreds of thousands of households from energy. Because the attackers were in the system for half a year. So this kind of like detection that there is somebody, especially for critical infrastructures where they can be caused by a terroristic attack, ongoing for months to opening the back door, it is very important to actually monitor the right information and being able to analyze that monitored information to understand what is happening, where is it happening, have certain threshold and decision mechanisms in place. So we have collected these, and these are present then in the table. Then the next phase, very important one, is the containment. So really how to stop this problem from propagating. And that is something that is really happening in existing systems in the state of the practice. You may have heard, again, there are many cases of systems where, for example, I think it was Amazon, where by an error, all the prices were changed to 1 pence. And although this has been known, the software developers were not able to stop it. This was just like all running through the system. The packages were actually packaged and delivered for this price, because once the problem starts propagating through the systems typically do not have pre-built mechanisms to contain the problem and stop it from propagating. So again, there are some mechanisms that can be used, and they are described then in different standards, because all these references are saying, look at this standard. It gives you details of like what you can do to prevent this problem from happening. And then there are needed pre-built mechanisms for recovery and then for the forensic analysis. So I think it's a very interesting direction actually to look into this kind of like more integrative knowledge that would direct the architect to the sources to study. Because there have been studies, empirical studies with teams, for example, education teams and cybersecurity, discovering that when you do these games that you play with cybersecurity expertise, it's not really cybersecurity experts who win in these games, because they tend to forget essential elementary things by focusing on something that is requiring more in-depth expertise. We are just human and we tend to forget. So having certain checklists in software engineering are quite a crucial thing still to have. Okay, so that is just an idea I wanted to bring in, and yeah, if anybody has a question, I'll be happy to take those.
Thank you very much. Very nice. I love the checklist on the glove. A very expensive way of doing a checklist.
Yes.
Those gloves cost about $40,000 a piece. So Anyway, thank you very much. Do we have any questions? You did mention that you'd be interested in having somebody take this up and move it forward. You don't have any plans to do that yourself?
I actually have a plans with some of the students that could take a look in those like different PCs. But from the point of view of my research, we typically as researchers go in depth of a thing, right? For this project, this idea, it was really like we would need something that is like going in the breadth, so that we know we haven't forgotten something important. So it's something that is like rather very useful for me for teaching the students and for working with industrial partners. It's not a research on its own, but yet yes, like with the students, I would like to look into extending the checklist and mainly validating actually the checklist with the people from industry. I think that will be very interesting.
Good. Yeah, very good.